And we are ready to go. This is Eric, everybody, and I'm not going to waste any more time. I'm going to let you jump right in, if that's all right. Okay, thanks for being patient, everybody. Here we go.
Okay, so hello, everybody. I am Eric. Thank you very much for the invitation today. So today I'm going to talk about one part of my postdoc at OSU. So I did my PhD in Japan, in the city that was in front of the 2011 event. So most of my professors there had experienced the tsunami itself. And I want just to try to transfer some of these ideas that or that were learned from the 2011 event here for our better understanding of the tsunami event, of a tsunami event in Newport. So this is a 2011 Tohoku-oki earthquake and tsunami. So what you see in the screen is basically the wave amplitudes or the waves that the tsunami or how these waves behaved in the Pacific basin. So basically, it reached out through all of the basin. In some places, such as in Chile, there were waves more than 2 meters or 6 foot. So big waves. And of course, here in the Pacific Northwest, you also had some big waves in very specific cities, such as Crescent City. So when you think about the specifics of the 2011 tsunami impacts, of course, the first thing that you think about is the Fukushima accident, right? Because that was a worldwide known impact, but also about 10,000 people died and more than 1 million people were evacuated during 15 minutes, during the first 15 minutes. But also, when you see the aerial photographs, you can see that the tsunami wave basically wiped out all these houses in this city called Natori. This is next to Sendai. But also, you can see that there are some changes in the colors in the image. You can see, for example, that the beaches are flattened or destroyed. So you can see how maybe I'm going to use this. So you can see how the beaches were destroyed here. And then you also see that not only the houses were wiped out, but also the sediment from these beaches was moved from the beaches to the cities. So at some point that had to be cleaned up. And when you think about the sediment, it is not only the sediment that was removed from the beaches, but also underwater, there was a lot of sediment that was moved from the nearby structures, such as the port structures. So in this city called Hachinohe, which is in the north part of the Honshu Island, this is the Honshu Island. In the north part, there is Hachinohe. So in Hachinohe, the tsunami moved around 15 meters of sediment. If you think about that, it's 15 meters of sediment, like of thickness of sediment, removed by a tsunami event. Like, let's think about 3-4 waves in 6 hours. So that's a lot of sediment. As far as we know, because this is the measurement after the tsunami, after the 2 or 3 days of when the tsunami occurred. So we don't know if that is actually the maximum Scour next to the port. It could have been more than that, and probably it was more than that. So 15 meters of sediment removed from the ports. But that was not only in Japan. That happened here in the U.S. So in Crescent City, up to 6 meters of sediment was removed from the port area. So that's a lot of sediment again. And at the same time, in the south part of Japan, up to 9 meters. So you have the same behavior in the two sides of the ocean by the same event. So this is important. And sediment is not only important because it's taken from one place and removed to another place, but also because when you have or when you think about the sediment involved in the tsunami wave, that changes the wave itself. So if you think about clear water, you have one wave that is clean and has some weight and has some specific characteristics. But when you have the real case of tsunami waves, you have waves that are coming to the beach and are eroding the landscape. And then you have all this sediment into the wave that mix up, and then you have these black waves or gray waves. But so that happens, what happens is that when you have this inclusion of these morphological changes and sediment transport, you have a change in the calculation of the tsunami wave by up to 20%. So if I run a simulation, a numerical simulation of a tsunami inundation without sediment transport and morphological changes, my map would be probably underestimated by 20%, and that's a lot if you think about a specific map of a city. That's a lot. So we have underestimation when we use this fixed bathymetry, and not only that, but also when we have sediment transport included in the tsunami simulations, we also have different depths, flow depths, of course, because the wave is, imagine that you have the first tsunami wave, then that wave flattens the landscape. So the second one is coming like in an avenue, so everything is flat. So probably the second wave is going to have a different flow depth and a different behavior. So those differences are, for example, in Japan, were calculated of about 1 to 2 meters with simulations without sediment transport and simulations with sediment transport, and flow speeds of up to 2 meters per second, which is also quite a lot when you think about that in terms of hazard. So my point here is that morphological changes are important, and sediment transport is important when you are thinking about tsunami hazard, and that has to be included in the schematization of the tsunami hazard. But not only that, when you think about the ports, you know that if you have a port like in Newport Port, you can have a scour next to the port docks that can create problems for the port operations, but also in the Aquina Channel, for example, if you have erosion at the bottom, that's going to be good for the big boats, but all that sediment is going to be moved to other place where it is not going to be good, and it's going to affect some effect on the navigation of the boats that you have here. Of course, you have the debris mixed with these, and this scour also affects the protection structures such as the jetty, as I'm going to show you here, and utility pipelines. For example, as we will know, we have water pipelines going below, deeper into the bay. And in some places, you would have remobilization of contaminants and debris. And finally, of course, we have salt water coming into our landscape. That means that we will have also some soil salinization, among so many other things that tsunamis bring. For coming back to the 2011, so sediments are not only a problem for hazard assessment, but also a money problem. So if you see this image on your left, on your right, sorry, you have, of course, the firefighters trucks, the fire trucks, and then you have also the debris of the houses, which is sometimes what catch up the attention. And then also you have all these dark mud and sediment. So that sediment accounted for about 40% of the whole disaster waste. So 40% of the waste was related to tsunami deposits. In Japan, in the 2011, that was about 11 million tons. And to clean these tsunami deposits, Japan had to pay about $5 billion just for 2011, just for, I mean, like in 2011. So if we convert that money for now, for today's money, that's gonna be more than 7 billion or something like that. So that's a lot of money for cleaning up the tsunami deposits. So and that's going to happen in the Pacific Northwest if you ever have a tsunami in the next 50 years. You would need to clean that up for sure, and then you will have to pay for that. That not only happens for tsunamis, but also for hurricanes. If you go to Florida, they are paying a lot of money every year for cleaning up the streets from the deposits. And in 2004, with the Indian Ocean tsunami, about 1 billion was calculated in damage to critical infrastructure in countries such as Sri Lanka, and critical infrastructure includes roads, railways, power telecommunications, and ports. So in Japan, you have Sendai Port, which is the place that was most famous for that. And then you have Fukushima in south, over here next to Onahama Port. So Onahama Port is next to the Fukushima power plant. And then you have a Kamaishi Port in Iwate over here. And all of these ports had problems during the tsunami. And the problems were related not only to the tsunami wave, the inundation itself, but also to the scour. So they had problems in the navigation channels, problems in the docks, and problems of sedimentation inside of the ports. So all of these ports had these kind of impacts. So in Japan, they had to pay about $100 billion related to coastal dikes, tsunami seawalls, gates, breakwaters, and forests, coastal forests that were impacted by the tsunami in a mix of the tsunami wave itself and the tsunami deposits. So that's a general view of why we are talking about sediments here, about tsunamis and sediments. So what about the Pacific Northwest? So the Pacific Northwest, just to, you know more than me, of course, but a general idea is that we have very important ports here. We have Newport, we have Astoria, and in Washington we have Grace Harbor and Anacortes, which is not only a port but also a refinery. And you move a lot of money here. You move from probably I'm wrong, and I'm sorry if the figure is not okay, but let's say about $300 million of every year contribution to the GDP is moved in the Newport area. Then you have in Astoria similar figures. Then in Grace Harbor you have a lot of freight that is being moved through the port, and also you have about $6 billion in value added by the Anacortes refinery. So in general terms, when we think about this Pacific Northwest, is not only the people, which is the most important part, but also, of course, the economy, because after the tsunami, you would need to, you need a country to run, and then you need economy to be able to progress. And so you have to try to understand better this to protect your economic ports. So what we are trying to do here is to develop a framework to model dynamic tsunami-induced scour. That means that we want to understand how, including sediment transport in tsunami simulations, help us to understand better how this dynamic landscape would interact with the tsunami waves. And in that sense, how this interaction between tsunamis, the sediment, is going to affect the critical infrastructure that you have here. The lifelines, for example, the water pipe that is going under the bay or the bridge itself. So what you have in your screen is a map, a very old one, but a map that has some of the lifelines that are going or that were going before under the Aquina Bay. So you have a lot of pipes that are buried in there, and then also you have the bridge, and then you have some specific infrastructure such as the port itself. And then you have also this beautiful bridge and the jetty. So to do so, we started by doing the typical one, but you know, is a very big earthquake that generates a big tsunami. And this is the expected or the simulated tsunami inundation scenario by Dugami, which is a large one, the large size tsunami. So we took that one, a similar one as the input to our model. And as I was mentioned, we included in the simulation the position of the pillars of the bridge and also the beautiful jetty that we have protecting the Aquina Bay. And all these dunes over here are also included. So we wanted to know how these would be affected by this dynamic interaction. And then we also included the some of the utility lines and port structures that you have. For example, this was provided by the city of Newport, and this is the water line that is going under the water pipe that is going under the bay, and this is the other one. So we also included that in our analysis. So what did we do? So basically, what we did was to use a numerical model called Delft3D, which is developed by the Dutch. And in this numerical model, you are able to include the tsunami hydrodynamics itself. So you are able to propagate the tsunami from the source to the coast and then inundate, and that's the deflow module. But also you have this demorphology module that basically what it does is to generate the morphodynamics. So how the morphology, the landscape, the topography is interacting with the tsunami wave and how that is changing over time. And that's important, as I was saying, for understanding how the whole tsunami affects the landscape. This is more technical. We reach 1 meter resolution near the bridge and near the bridge mainly. We use some scenarios in which we change the roughness because, as you know, if you see this map on the right down, you have different types of landscapes. So in some places you have forests, in other places you have urban development. So we use that as a reference to modulate our roughness scenario. And then also we have different thicknesses of sediment. So the model would be able to try to understand how different thicknesses would change the tsunami impacts. So in general, we simulated 8 scenarios. And then we just compared our results with the state and the Dugami models to see where we were located. So these are the results. So what you are seeing there is a simulation result of morphological change or topographic change, but bathymetric change. So what you have there in the top is the time. So you can see that we are running from 0 to 180 minutes. So that's 3 hours of simulation. So we are simulating here 3 hours since the tsunami started. What you have in the red colors is sedimentation. And what you have in blue is erosion or scour. So basically, what you are seeing here is how the tsunami waves are mobilizing all this sediment. In black, you have the shoreline. So we are going from north to south. So we have the shoreline over here. Then you have the north-west jetty. In the south, you have the south-west jetty. Here, for example, where the mouse is in the marina. The bridge is over here where I am pointing. We are in this area, and then the port is in this curve over here. So what you see in general is that the tsunami, as I was mentioning before, it is eroding the Aquina Bay mainly. where you can see this blue. So the blue means that the tsunami is eroding the Yaquina Bay, and then it is taking all these sediments from the bottom of the Yaquina Bay to the sides of the Yaquina Bay over here. So in essence, we are moving sediment from the bay, from the bottom of the bay to the port and to some of the, mainly to the ports over here. And there is this very specific point here in the corner that is getting dark blue. That's the root of the jetty. And that was important for us because one of the things that we saw is that the jetty is vulnerable to breaching due to the tsunami. And that modulates a lot the tsunami hazard for Newport. Anyway, so this is the general result. Again, blue colors means erosion, and white colors or yellow colors means sedimentation. So we have here the tsunami-induced morphological change. This is very specific, and this is very technical about how the scenarios are influenced by sediment composition and roughness. But for the general understanding, what it matters here is that we have two extreme scenarios here. At the top, we have the most extreme scenario. I mean, we have the same tsunami in both cases, the same tsunami waves, but we have different sediment configurations. So in the top case, we have the most extreme scenario, so the highest erosion and the highest sedimentation, and at the bottom, we have a more conservative one. But in both cases, what you can see is that, again, you have this strong erosion at the bottom of the Yaquina Bay, but also you have this breaching of the jetty, the North Jetty at the root. And that is important because if you see this blue is depicted as a somehow like a more straight line, right? So we are having something like it's breaching this, and it is cutting the road from instead of going all the way through the Yaquina Bay, it is cutting over the bridge. So that means that the first wave somehow it's affecting this jetty and reducing its capacity to contain the tsunami itself, although it wasn't designed for doing so. Anyway, and then you have also the sedimentation. You have the sedimentation next to the ports, the port infrastructure, and then when you see this Hatfield Marine Science Center area and the South Newport area, you also have some erosion at some points, and then you have some sedimentation too. And that is important, again, in terms of cleaning up the tsunami deposits. Also, we have some changes in flood depth, and that means specifically changes in the hazard map. In the most extreme case, you have changes of about 1 meter to 2 meters in the South Newport area and the Hatfield Marine area. And in the more conservative one, you have changes of about 0.5 meters of flood depth. And that is important depending on the specific point that you are seeing. For example, one thing that we did was to see if that was important for this building. And the change at this specific building is not that significant. It's just a matter of centimeters, tens of centimeters, which is not, it's within the range of uncertainty. So for this building, it's safe. But for other places, it could be important because that means that some of the buildings that were previously evaluated as that were going to resist a tsunami or withstand a tsunami probably are not going to now. So in any case, this is research, and this is just a guide to tell us that it is important to include sediment transport in tsunami evaluation. Going back to the jetty breaching. So again, we are going back to this image. So what you have here, so this is the bridge. Probably you can see the line of the bridge over here, and then you can see some spots. These spots are the pillars. So the pillars, you can see that, for example, the tsunami wave is eroding more between among the pillars, the bridge pillars, but it's also generating some sedimentation in front of and behind the bridge pillars. But one question that we have here is that if this scour next to the bridge is going to be important for the bridge resistance or resilience capacity, and that's an open question that probably we are not going to solve here, but we do have some scour next to the bridge that has to be better understood in the future. But for here, what we did was to see the capacity of the jetty to being or the vulnerability of the jetty to being breached. So according to the numerical simulation, there is going to be a strong scour over here. And then what we did was to we went to this yellow point over here, which is the picture that you see there. And then we calculated if the tsunami wave was going to not only remove all the sand on the dune, but also these rocks, which at first look like very big rocks. But when you go there and you calculate what is the size and volume of each specific rock, you can see that the average diameter of the rocks are about 1.2 meters, so that's 4 feet, right? Yeah, about that. So they are not that big. So I mean, depends on the point of view, but it is about that. This diameter about 1 meter and something, and the volume is about 5.1 cubic meters. So we just use a formula that was developed by a professor in Japan, Hanzawa, after the 2011 event to see this tsunami that we have as input for our simulation in Newport, if that tsunami was gonna move the boulders or the rocks that we have in our jetty. And what we have is that this is time on the x-axis. So again, we have from 0 to 180 minutes. This is in seconds, so it is about 3 hours in total. So what we are doing here is just having what is the relative tsunami height for that specific yellow point that I showed you before, and then to see if this Van der Meer parameter that was modified by Hanzawa. So the key point here is 3. If these lines go over 3, that means that the boulder is going to move. And what we are seeing is that for boulders larger than 7 meters, they are going to be stable. But if they are smaller than 6 cubic meters in volume, they are going to move. So if we go back to the plot, we can see that most of our boulders or of the rocks that are conforming this jetty would be probably moved by a tsunami wave. So that means that we are now telling some of our stakeholders, such as the Army Corps, like we need to think about this jetty as needing future reinforcement or at least more research on this, because it could breach. What about the pipes? So this is the location, approximate location, because we couldn't have the exact location for security reasons, but this is the approximate location of the water pipe line going under the bay. So this blue line is the current bathymetric profile. So that's the current depth of the, or at least by the time when the bathymetric survey was conducted. So that's the profile, and this is the results from our 2 extreme scenarios. So the dotted line is our more conservative one, and the dashed line is the most extreme one. So in both cases, you can see that the pipe is exposed under these circumstances, but how much is going to be exposed depends on these specific parameters that we have here. Anyway, what we are trying to show here is that we could have some pipe and seating for the water pipeline line under the bay, and we already showed this to the city, and I understand that the city, not because of this, but because of other reasons, they are also changing the water pipeline, which is going to be deeper, way deeper. What about sediment on the docks, on the port docks? So what you have there is on the left, we have the Army Corps map with the infrastructure for Newport, and you can see all the description of the port docks. So what you have is that in this area, you have most of the infrastructure in the north side of the Yaquina Bay, but also on this side is where you are going to have the higher concentration of sediment, or you will have a higher sediment remobilization. So that means that the port operations would be affected by this sediment transport induced by the tsunami, and they will need to pay for that at some point. And that has to be then evaluated for their operations themselves. What about the sweeping? How much is going to be, how much Newport will need to pay for sweeping the south part of the city? So for this black polygon, we calculated how much sediment in our more conservative scenario, and our on both in the more conservative and the more extreme scenario, we calculated how much sediment would be needed to be cleaned up, and we calculated that about the city would need to from $8 to $38 million to clean this up based on the standard calculations that FEMA uses for cleaning up or removing sediments for hurricanes, which might be fair, but still we are talking about millions of dollars that the city needs to include in their assessments. And finally, again, tsunamis are not only clear water or salt water. They have a lot of things, among which you have sediments and debris. So this is a cascading failure map that we are trying to develop. So we have a lot of mistakes here. And if you want to contribute, you are more than welcome. But at first, we think that this could be something like that could give us an idea of what we have. So we have a tsunami, and then this tsunami is generating some jetty breaching that it's also feeding like feedbacking the scour and the instability in the bay, which is going to lead to pipes and cables and seating, which is going to lead to service outages, power, water, and telecommunication degradation or outages. Also, if you go back to this scour, as I showed, you would have that this scour and sediment remobilization would create port disruptions, fuel and supply interruption, of course, because you wouldn't have trucks coming to the south part of the city or to the north part itself. And that's going to lead to economic and social disruption. Going back to the sediment deposition and debris, again, we have this feeding to the port disruption. The tsunami and the morphodynamics also would restrict the breach. And in general, this sediment on the roads and the bridge, loss of use would lead to an access loss. So you wouldn't be able to communicate the north part of the city to the south part. And of course, that's going to lead to accessibility loss. So you have this complex interaction among all of these elements that are needed to be think of. So I think that this is we think that this is an important part that needs to be worked on in the following decades. because we have this hybrid cascading model where we have several cascading hazards from a single hazard that could be the tsunami. And then you have on the left all these things that are happening that are going to create some of the effects on the right. And if you have all these multi-layer probabilistic time-dependent map, you will be able to have better decision tools because you will be able to decide if, for example, you need to improve or reinforce your jetty, or if you need to, for example, change the water pipeline that is going under the bay. So that's a general idea of what we are thinking of this as a decision support tool. So we are expanding this work to other places in the Pacific Northwest. And in that aim, the Pacific Northwest Waterways Association is helping us, thanks to Paula from the Newport Port. She's supporting us to go as part of the summer conference of the Pacific Northwest Waters Association, which is going to be here in Newport. And at the same time, we are expanding this methodology to other ports in Astoria, Grace Harbor, and Anacortes Refinery. And we are thinking of how to quantitatively map these cascading effects into, for example, hazardous materials release or electric outages. And also we are thinking of course, smaller sources and probabilistic approaches that also include these far field tsunamis that are more probable than a large tsunami here. Some of our stakeholders, the Dogami, of course, the Department of Geology, the Emergency Management Division of Washington, the Pacific Waterways Association, the City of Newport, and the Port of Newport. They are very, very kind people to us, and they have provided a lot of information. And this research is supported by CRESCENT from NSF, also from the COPES project from NSF. The NIST is also paid for the first part of this research and my salary. And the Cascadia Lifelines program also is helping. And this is now a collaborative work with COAS and College of Engineering, because we just, like last week, we got some seed money to start thinking of coastal solution sandbox, in which, in general, the general idea here is that we want to have like a game engine, like gaming. Like if you go to, I don't know, to play one of the PlayStation games, I'm not very fond of that, so I don't know much about that. But like if you have, what it is important here is that we are trying to create this very interactive way of communicating these kind of things. So we can take people from the community and show this coastal solution sandbox to tell her, like, look, this is what a tsunami actually does in a real scenario, so we can improve our risk communication and the storytelling of the tsunami risk, because it's very difficult sometimes and we get too technical. Thank you very much.
Thank you so very much, Eric, and thank you for flexing with us. Incredible information. I know there's questions. So we're going to bounce back and forth between questions in the room and questions online. And just like when we were in the auditorium, please raise your hand if you have a question. So Roseanne, any questions coming in yet?
Oh, not yet.
Okay, so folks online, go ahead and use the chat box if you want to ask a question, and then I will come to Jody for a question.
So this question spans both the sediment model and the later things that you talked about, the cascading effects after a tsunami. Did you start with sediment that where it is today and bring a tsunami in? Or did you start with sediment and broken buildings, which would be there after the earthquake? For instance, the sediment characteristics are going to be much different just because of the earthquake. We're looking at liquefaction where we sit now, and that sediment will respond very differently than just dry sand.
That's a very good question, and I started with topographic and bathymetric data and geological data from past surveys. So this is not even information that it is current information, but it is a little bit old, like 2-year, 3-year-old information. And from there, we simulated the tsunami and the sediment transport without buildings. So we don't have the physical, like the physical inclusion of the buildings in the simulation. So we don't have that interaction between the tsunami and the building itself. That's first thing. So we don't have the possibility right now to tell how the tsunami is going to affect these buildings, standing buildings, or collapse if we are going to remove them. The second one, yeah, you're right. We haven't included the sediment characteristics after the earthquakes. So if we have liquefaction, that means that we will have a higher availability of sediments to be eroded by the tsunami. We didn't include that, and that's a question that we are getting a lot from a professor from University of Oregon, for example, Ray. But that's something that needs to be done in the future. I'm not sure if I'm going to be able, but that's something that needs to be sure to evaluate what is the effect of that on the simulation. Yeah. So research.
Other questions in the room? We'll get around.
Thank you for the presentation. I had a question about if we wanted to look at like the surrounding areas, not just necessarily the port, but maybe just a little bit further south, or like Walport, or going up to the Silettes. Do you have this posted somewhere where we can kind of like, or an interactive that we can kind of zoom in and look at kind of sediment transportation for, let's say, some of these other smaller locations, but are still within the county that might be, pertinent information for people to have?
Currently, we don't have that online. I'm gonna upload these maps to OHealth, so you can check the information for Newport, because we didn't run the simulations for a larger area that can this is the area that we are processing basically. And it was a constraint on the numerical these models are very expensive computationally speaking. So we didn't include a wider area. A little bit south, but no, I think it's not useful for those places. And that's something that needs to be done in the future.
Okay. Thank you.
Thank you.
So this is really fascinating. I was wondering, with the breach of the dike there, the North Jetty, do you know, is that as historic? Are there old maps of Newport showing that that may have been one of the exits for the Yaquina River? Because I mean, the Yaquina Basin has been shaped by tsunamis in the past, right? I mean, this is not the first one, and maybe there was already a river channel historically that got filled in when they put the jetties in. Do you know?
I don't know, and that would be very interesting to check. Right, for example, for air photographs from the 50s or before. I understand that the jetty is like from the 60s or something like that. The first parts of the jetty were from the 60s or something like that. So yeah, I don't know, but that's a very good point.
Yeah.
There's an aerial photo in the hallway around the corner we can go look at.
Eric, thank you very much as well for that presentation. I want to follow up on what Lori was talking about. Can you clarify, so in that breach on the north side of the jetty, was that breached during ebb flow, of the flow flowing out from the bay?
Probably this is let's see. So yeah, this is the first wave coming. So you can see that this is at least the tsunami is starting to erode the dunes from the very first wave. And
But it's
then
not coming from the ocean over the dunes, it's coming from the bay out.
it is coming from the ocean. Yeah, it is coming actually from the, if you see, these are vectors, these are velocity vectors. And if you see, for example, the vectors here, the tsunami is coming from the north. And then like maybe there it is here. So it is coming from the northwest and then like creating some kind of like turbulence over here, like some curve, like it's changing direction in this specific point. And the reason is that we have here the cliff, right? So the tsunami energy is somehow redirected to the south, but then also you have all these tsunami waves coming from the south.
So all those little gray points, there's no vector on it. Does that mean there's no flow at that point?
The velocity, the instantaneous velocity at that point is zero for like we have so many velocities at the same time that it is not accounted for. But so this is the net velocity. So this is like the way that is flowing. The tsunami is flowing in the bay. So yeah, but for your question, the first wave it's the one that starts to erode the dunes, and then the jetty starts to breach, or the rocks forming the breach. The jetty, sorry, can be moved from the very first wave. For example, for boulders smaller than 1 cubic meter, they are moved from the very first wave. But then for example, for larger boulders such as 6 meters, they are moved after the third or by the third tsunami wave. So it depends on the volume.
Roseanne, looks like we have a question online and we're going to get close to the running out of time.
I have a comment online, and it says, check the Gwynn Library for maps from the 1890s. There was a small jetty on the south side to accommodate the railroad, and there are also car maps from that era showing depth.
Okay, thank you. We'll do that. I didn't know that.
Great. Yes, Steve, you can have one more.
Can I ask one other quick question?
Yeah. As
On your second slide, can you pull your second slide up?
my second one?
Yeah, very second. So. In your introduction on that, so the tendril of high energy that hit Oregon and Northern California right there, trace that backwards if you can with your finger. It deviates right there. What happened right there? What made that?
Thank you, Steve.
That's a good question. I don't know the answer right now. Probably there is an island there or something like that channel, like a submarine mountain or something like that. But yeah, there is a fissure that generated. Yep. Yeah, that's a good point. But it must be something in the floor of the ocean that it's changing that. Probably it's because of these are the Emperor. I think it's the Emperor Islands. Anyway, you have the Hawaii here, right? The hotspot, and then all these sub-oceanic islands are going like this and then like this. So probably it's one of them that is redirecting the tsunami waves to the Pacific Northwest.
All right. I think this room could talk to you forever, but we're going to wrap it up for those folks that have other places to be. And just one more round of applause for Eric. And everyone, thanks for being flexible with us today, and we'll see you next week. Thanks all. It's like, what were you saying?
Shows the water over Newport area, how you first flood modeling that.
That brings my mind, and I've seen that mineral. I mean, I thought they had that.
This one's no, my mom's. Okay. That's not mine. This is the tsunami inundation scenario from Dogami. So this is the Department of Geology
Oh, okay.
tsunami map.
Tsunami. Well, sure, that one specifically.
You can go to the Ducati website.
Okay.
And there you can check on all the scenarios. This is large size. I don't know if you're familiar with this. They decided to size them like t-shirts. So they are going from small to extra large. So this large size is particularly important for me because it's the largest inundation.
This is my house, right?
All of them.
There. And also what we talked about in our answer, how do we get to Highland? And there's these spots out here that I could run through the park to, or we could try to come up to this neighborhood here, which sets up
That's probably
high.
safer. And probably that's within walking distance from here. We have like 18
And we teach away. A lot of direction, but then there's nothing. Yeah, or we can move, or get to the airport, but, yeah, that would be the way, maybe we'd have to run out to the beach and then come back up. That's kind of the opposite direction.